Hello and welcome to our today's webinar about the application of computational fluid dynamics for the optimization of an EGR valve. My name is Milad and it's a big pleasure for me to be your today's host. I'm the product marketing manager at SimScale, and as a part of my role I'm conducting and organizing different workshops and webinars on a regular basis about different topics, and with these webinars we try to introduce new and interested users into the world of engineering simulation and show them how simulation can be applied within their industry. Before I joined SimScale, I've gained a lot of experience, more than 10 years, working on different projects as a simulation engineer and consultant in different industries like automotive, as well as aerospace and biomedical engineering. Before we start to dive into our today's topic, I would like to quickly discuss our agenda with you. So we will start this presentation with a short and crisp introduction to the general world of simulation. So we will talk about the general benefits of using simulation, and I will introduce you to SimScale, our web and cloud-based simulation platform, and I will explain you how you can use our platform for your own simulation projects. Yes, and for the remaining time, we've prepared what we call a live demo. So it's a real-world simulation problem where we simulated the flow inside the EGR valve for different configurations, and I will show you how such a simulation looks like in the SimScale platform, and we will together discuss the results. And at the end we have a Q&A, so in the case you have a question, don't hesitate to ask me. You can write your question or submit them using our question toolbox, which is part of the software GoToWebinar we're using to broadcast our webinars. Yeah, let's talk first of all a little bit about engineering simulation, and first of all I would like to discuss what engineering simulation actually is, which is like the another word also for CFD. So a lot of times people, when they're talking about fluid flow simulation or finite element analysis simulation, they also call it engineering simulation. Well, and the best way to understand what engineering simulation actually is to compare it with analytical models. And we all know analytical models from school, and they are characterized by the fact that there is a closed mathematical solution for the entire domain of the model. So for the boundaries, as well as for every continuous point inside this continuous domain. And usually we use them in engineering only for very simplified applications, and they are usually also restricted by the mathematical solubility of the equation system. And a very good example for this is if we calculate a linear force on a spring, or where it's a relationship which is quite known, which says that the force acting on your spring will be proportional to the elongation, and the proportional factor is the spring constant. About another example, if we're talking about fluid flows, for example, is the law of Hagen-Poiseuille, where we simplify a flow to a two-dimensional analytical problem. And in contrast to that, there are a lot of problems from the real world which we cannot solve using analytical model. A lot of them because we cannot formulate it, but also because we can just not solve it. And what we do instead is we take this analytical models which we cannot solve, and we solve them using numerical techniques, which means we will just calculate an approximation of the solution at defined support points, and between the support points we need to approximate as well, or to interpolate. And this allows us to actually simulate very complex issue and very complex physical phenomena, but it needs appropriate models and algorithm, which means that you as a user need to decide which model you want to use. And in general, using simulation, a lot of advantages, because in reality it means that you have a kind of virtual test rig, or if you're dealing with fluid flows, you have a kind of virtual wind tunnel, and it allows you actually to improve your products or to design your products in a completely different way. First of all, it's much faster than physical testing. So if you just think about it, if you want to, let's talk about our example about a valve. If you want to physically test the valve, you need to manufacture the full valve, you need to prepare the test rig, run the test and analyze it. And this can take up to several weeks, this whole process. With simulation, we're not talking about weeks, but about days to hours. And later we'll also talk about the time investment for preparing such an EGR valve simulation. But usually, if you're an experienced user, the typical turnaround time is like between 24 hours. And actually, you can, in this 24 hours, you can compare and simulate as many design variants as you want in parallel. And this helps us because it allows us to enable failures, because, you know, at the very early product design sheds, we can test different concepts, and therefore it gives us much more flexibility to us. And in the end of the day, this helps us to reduce our costs. And from what I've told you so far, you must think, well, simulation is such a great tool. And obviously, the majority of engineering is using it. But the truth is, it's exactly the other way around. Actually, only a small minority of engineers has access to engineering simulation. And you know, there are a lot of reasons. And yeah, I think more than 6 years ago, SimScale was founded. And the idea back then was to democratize engineering simulation, make it accessible to everyone in the world. And back then, like, we tried to figure out what are the main reasons which are preventing engineers or small companies from adapting engineering simulation. And in the end, we ended up with three main reasons, which we also call barriers. First of all, traditional simulation tools are very expensive. You need to spend an upfront investment of about like 20 to 50,000 euro. And just, you know, to have the right hardware and software to be able, in theory, to run the simulations. But it's not only about the initial cost, it's also about a lot of the work and the resources you need to set up the infrastructure which is needed to run simulations. Because it's not as simple as installing, let's say, Microsoft Word. You need to set up a network with servers who can do the calculations. You need to set up a network storage where the data can be saved, and you need a visualization infrastructure using a powerful workstation to visualize your results. And the third reason, which is maybe the most important reason from my point of view, is what we call the know-how barrier. Most of the traditional simulation tools were designed for simulation experts, but not for, let's say, simulation novices who want really to solve the problem, who are working, let's say, on the design of a product and want to use it themselves. And yes, that's why we came up with SimScale, and since it's web and cloud-based, everybody can use it. You don't need to install anything. You don't need to buy any hardware. You don't need to manage any licenses, software, or update anything. You just need to upload your CAD model, set up your simulation, and take your design decisions. And I don't want to talk too much about SimScale, but I would like to raise some of the most important and I would say most unique points of SimScale. First of all, SimScale is what we call an all-in-one tool. So there is no differentiation between different license models, and usually when it comes to simulation tools, you need to buy every module. Additionally, let's say you're doing CFD, you're doing fluid flow simulation, and now you want to calculate how the temperature distribution of the exhaust gas, which kind of stress it will induce to your material. Usually you need to buy another license. SimScale, everything is inside one user interface, and everybody can use all algorithms and simulation tools. And due to its cloud-based approach, SimScale is super fast and easy. So you can run it on every device, you can access your result on any device, and it's much faster than using your own computing infrastructure, since you can leverage up to 96 computing cores for your simulation. Our cloud-based approach also allows us to come up with a completely new concept of real-time user support. We have integrated chat in our platform, and you can directly reach out to our user success and support team. And also one thing which I would like to mention, that SimScale is actually a free tool. So we have a freemium pricing model, and actually you can access exactly the same features like paying customers using our free community plan. Finally, before we start to dive in our today's topic, let's quickly take a look on the customers of SimScale and which kind of company SimScale is used. And we have a lot of customers actually from the AEC industry, so architects, civil engineers, which use our tools, to optimize thermal comfort and wind loading on tall buildings. But on the same time, we have also, more and more customers from automotive, which are, for example, using our simulation tools to design OEM equipment, and usually not the car manufacturers itself, but their suppliers are using our tools. And usually these kinds of companies did not access to simulation before. All right, and now let's start to dive into our today's topic. And first of all, let's talk a little bit about our today's example. So in the next 20 minutes, we will together discuss the results of a CFD of an EGR valve. And for those of you who are maybe in the valve industry but not very familiar with EGR valves or combustion engines, let me tell you a little bit about the background. So as you all know, there is a huge discussion right now, or for a longer time, about the impact of cars on climate change, on the greenhouse effect, and also about problems like smog and other fumes and pollutants in the air, which can really harm your health. And inside this discussion, we are talking also a lot about diesel engines, and actually it's a ongoing discussion. And one big problem with diesel engines is that they are creating two kinds of pollutants. First of all, we have nitrogen oxides, and these nitrogen oxides, they are really they can really create serious damage, because they can damage our lungs. They will react with ozone and reduce ozone and a lot of other stuff. And what you usually try to do with excess treatment is to manage your, let's say, burning conditions inside the engine. And with this approach, you actually can control the release of nitrogen oxide. And here the approach is that nitrogen oxide can only be, or will only be produced if we have high temperatures and too much of air. And the big problem with the diesel engine is that we actually have a heterogeneous mix from fuel and air, and therefore we have a lot of zones which are, let's say, air-rich. And the idea of EGR is that we will mix some of the exhaust gas with the fresh air, which is taken from the intake, and this will allow us to reduce the concentration of oxygen, and this should reduce the amount of nitrogen oxide produced during combustion. And this excess EGR valve, or excess gas recirculation valve, they are exactly designed to control this nitrogen oxide reduction. And you ask yourself, how can CFD help now? Well, let's first of all try to understand how this is actually working. So this is our valve in a cut view section. And let me see if I have something like a pen. Yes, I have. So this opening is going to the cylinder. This one is going to the exhaust. And this one is the air intake to the ambient. And what actually is happening is that I have my fresh air which is coming inside, and depending on the setting of the butterfly valve, And this valve, we can mix, or we can like control how much, or we can control the ratio between fresh air from the intake and exhaust gases from this direction. Yeah, and as you can imagine, with moving this part, I can control like the mass flow from the exhaust port, and with the butterfly valve, I can like manage how much air is coming from the intake. And now we can see several potentials for optimization, which we will discuss in the next step. And this is another view from the CAD model. Here you can see all the details. And now let's think where we can use simulation. Well, to answer this question, we first need to think about like what are the operating conditions, operating points of this valve, and what do we need, or what can we simulate and therefore optimize? Well, there are three modes actually. The idle mode, where the poppet is closed, so no exhaust gas can come inside this mixing pipe. And the butterfly is nearly closed, so we have like a little bit of air and no exhaust gas. For throttle, the poppet opens and the butterfly goes into a 45-degree position. And if we have the wide open throttle, this is, you know, on Automatica, when you like kick down the throttle, then this mode is activated where the poppet is closed and the butterfly is completely opened. And you maybe ask yourself, why is the poppet closed at wide open throttle? Well, if I really want to, let's say, run the engine on a high load, I actually need the oxygen. And EGR is mainly used for cruising conditions, where you just have semi-load, and there it's massively increasing the efficiency of the engine and reducing polluters. Yeah. And now we're going to investigate several things. We'll talk about it in 5 minutes, but just to let you know, we will use the CFD simulation like to take a look into the flow field. And first of all, we have to decide like which kind of boundary conditions we want to use. And in this case, we just took some data about the Skoda Fabia 1.2 HTP gasoline engine. It's just an example, you know, just to have some typical values. And so the velocity of the intake flow is approximately 0.8 meters per second. And we will model the amount of recirculated flow by applying 10% of this mass flow rate or velocity on this inlet here. And the boundary condition for the outlet itself is 0 Pascal, so which is the gauge pressure, the ambient pressure. And so the biggest simplification is that instead applying here the pressure profile of the intake port, we will just apply a fixed velocity of 0.8 meters per second. And this will now allow us to optimize our valve based on the three aspects. First of all, after running the simulations, we can visualize the flow, and this will help us to identify flow conditions which are counterproductive. And if you think about it, the main job of the system is to ensure sufficient mixing between the air and the exhaust gases. And here we can see and with the help of these visualizations, we can observe the flow structure and leverage potentials for optimization. Another thing which is very interesting, because when you visualize the flow conditions, we really want to take a look at the static points, but usually during the valve operation, when we switch from one to the other valve state, we will have some transient phenomena which we can also like investigate with the help of simulation. And finally, we can also try to optimize the design, and we'll test different puppet head designs. Well, first of all, let's switch now to the SimScale platform. So this is the project I've prepared. And everything I'm doing here, it's inside the web browser. You just need to log in. And first of all, let's take a look at the geometries inside this project. So this is the CAD model of the valve. We have also some other models. First of all, you need to create the flow volume. This can also be done with the CAD system, but you can also do it at SimScale. And the next step is what we call meshing, and it's about, creating this mesh, so dividing your continuous domain in discrete parts, which a computer can be calculated by a computer. In this case, it was done manually, adding different kinds of refinements. And once this is finished, you just need to set up the actual simulation itself. So choose which kind of simulation you want to run. In our case, the incompressible flow simulation. Choose the mesh you want to use, the domain, the material properties of your fluid, and the boundary conditions. And then you can just run start a simulation run, and even take a look at the 3D results through the web browser. Yeah, and first of all, we will take a look at the flow behavior through the main valve body when the puppet is closed. And let's see if we can detect some zones where the design should be optimized. And if we now take a look in the near of these two valve bodies, so when the puppet is open, we can see that there is already some mixing. But we really need to make sure it's enough mixing, because the effectiveness of the EGR really depends a lot of the mixture between the exhaust gas and the fresh intake flow. And now let's try to understand what is happening. Sorry, it was too quick. And here you can see we already have a kind of flow separation behind the butterfly valve body. But since the exhaust gas is coming from this side, it would be great to have some more mixing on the opposite side of the puppet. And here we can see the results of a simulation where we try to simulate the non-stationary behavior while the EGR is being activated, so while this puppet is moving. And we will now test how we can influence that by, testing different puppet head designs. So it's the initial design, and we have this new design here. And let's take now a look at the results. So first of all, let's take a look at the wide open throttle operation point. So the EGR valve, it's actually closed. And first of all, the color map here is showing us or representing the velocity field of the flow, and we can observe two things on the first view. First, so we have here two kinds of flow separations. One is on the inlet side here, of the intake side where the flow is coming in. It's due to the elbow. We have an ununiform flow profile, and the same we have it actually at the exhaust part of the EGR, which is going to the intakes. Oh, sorry. And if we now zoom and take a look at what's happening in the near of the puppet, so this valve is closed, we can see that there is a huge large created by the puppet, and this will create a pressure drop down and again a non-uniform flow. At the same time, we have some wake which is caused by the butterfly, but this can really be neglected since it's really small compared to the wake generated by the puppet. And if we now compare it with the idle mode, not only the puppet is closed, but also our butterfly valve And actually this leads to very low flow rates, and yeah, and in this case, you know, pressure drop and velocity profile are not so important, since the flow is mainly constrained by the butterfly. If we now compare both, let's say, states, so on the left side we have the wide open throttle, and on the right side it's an idle. You can really see that the whole flow structure is changing, and especially that also the wake behind the poppet is massively impacted by the butterfly valve. And now let's take a look at the throttle setting, or throttle operating mode. So poppet is opened and the valve is not completely closed. The butterfly valve is not completely closed. And here we can observe that first of all, if you compare it with the other images, the flow is massively accelerated behind the butterfly valve. And we can see that there is a kind of interaction. So part of the flow is going inside the exhaust gas pipe and streaming back, as we can see here again. And the flow is accelerated here and decelerated when leaving the poppet. And whenever it comes to mixing, and that's an important point, you can see that we have some wake here, which will definitely create mixing. However, for better mixing would be I would prefer, you know, to have also some higher velocity gradients inside the flow. And here we have high velocity, and therefore, where the velocity is high, according to the law of Bernoulli, the pressure is low. Yeah. What is also very interesting is that with here you can see, like, we compare the three different states, and you can see how this high velocity, low pressure zone is like moved down by the position of the butterfly. So first it's here, then it becomes bigger as more as we close it, and once it's completely open, the valve, we become a high and a low pressure side. Also, we can see that there is some interaction between the components, and that, for example, this fast jet stream will flow around the body, the cylinder where the poppet is which is moving the poppet, and therefore we also have two separation bubbles here and here. Now we're going to compare the two different designs. So on the left side we have the initial design, on the right side the new design. And the first thing which we can observe is by using this new geometry, more of the flow can flow through this gap, since we don't get this high pressure gradients, like and the flow does not need to be accelerated so much in y direction. And we get also a kind of jet stream here, which will help us with the mixing here to mix exhaust gases and airflow. And actually, if you think about it, it's really like that the flow here can't follow this deep profile, and therefore we have the separation here, while when we have this new design and we have this jet coming out between the gap, the separation is happening much later. Yeah, now let's try to compare the forces. And this is very interesting because independent from the, let's say, shape of the poppet head, the forces actually stay the same. And yeah, this is related to the fact that the aerodynamics or the fluid mechanics and flow structure inside this valve is mainly controlled and manipulated by the butterfly valve. And this one is very interesting because this is our transient simulation. And this is interesting because it seems like for stationary conditions, it doesn't make a difference. But if we take a look at the process of changing the state or the operation point of the valve, there's a big influence between the sharp poppet head and the flat poppet head. And in the end of the day, our application engineers invested 4 hours of manual time to to prepare the CAD model, to upload the simulations, to mesh everything and run the simulations. We took an additional 6 hours for computing time, and since we used more than one core, in the end there were 420 core hours used. So the total turnaround time for the simulation is 1 day, 10 hours. And in return, we saved a lot of time compared to physical testing and saved prototyping costs. We were able to improve the design and also identify areas where yes, the valve can be optimized. Yeah, thank you very much. In the case you have questions, you can write them now into the question toolbox. I already tried to answer most of the questions during the webinar. Yeah, thank you for being here with us. It was a big pleasure. And let's see if there are some more questions now. Michael wants to know which turbulence model was used. Well, Michael, for this simulation we used the K-Omega SSC turbulence model, which have been validated a lot of times by our application engineering teams and researchers and scientists around the world. And yeah, that's the turbulence model we've used. All right, seems like I answered all the questions. Thank you very much for being here with us. It was a big pleasure. And in the case you have questions, don't hesitate to contact me by email. Have a nice day. Bye.